in January, February. And in fact, he did say that.
Okay, good afternoon, everybody. Thank you. So my name is Sara Bonella. I am Deputy Director here at Cecam, and it is my pleasure to welcome you to this first conversation in our series of conversations named after Marianne Mansigh. We have an interesting afternoon ahead of us. My job here is to act as mistress of ceremonies, which means that I mostly have unpleasant duties, keeping people on time. And these are also duties that I am usually very bad at, so you will see how it goes. One thing that we really like at Cecam and Marble, that is co-organizing with us this conversation series, is to focus on content and try to keep interactions as informal as possible. So please feel free to ask questions whenever you are given an opportunity to do so. I will be illustrating a bit more in detail the program for the day in a few minutes, but we would like to start with a welcome and a few words of explanation on our intentions from Ignacio Pagona Barraga, who is the director of Cecam.
Okay. Thank you, Sarah, and thank you again for coming here. As Sarah says, this is a series that we organized together with Marble, and that we decided to name it after Marianne Mansigh, who was actually the person who gave the first, was invited for the first of this series, the first event, and who was one of the pioneers in really making work scientifically with high performance or high level computing centers at the very beginning after the Second World War. Today we have with us Massimo Noro, who will be introduced later in more detail, and who will be talking about computer modeling within the industrial context. As I said, this is a series that we decided to start together with Marble. For those of you, just in case we don't know each of these two organizations, Cecam is a center that has been working to catalyze research within computational modeling for now 50 years. And since 2008, we have our headquarters here in the EPFL. Basically, we promote fundamental research and computational methods through our core activities, who are organization of especially workshops and schools. And we also try to trigger additional type of events to promote computational science and to raise awareness. And this is one of these additional type of events. And we decided to do that together with Marble, which is a national center of competence in research, in particular in materials revolution, computational design and discovery of novel materials. This is a project that is coordinated here at EPFL. It has been ongoing for 5 years, and it will be still ongoing for another 4 years. And being both in campus and being both initiatives strongly committed with the science and the development of computational models, then we try to build together, and we had the idea to try to organize this here in campus, serving both type of communities. So this series we decided to initiate because of the profound impact that computational modeling has had in science, in technology, in the society. And we thought it was, normally, as I said, for example, at Cecam, we organize scientific activities, we organize meetings for people to work together, but we thought it was also good to have from time to time the possibility to kind of step back and get a broader perspective of what is the impact of what we are doing and how in the last 50 years this has really developed and affected many other aspects of our life or in our society. So basically with this series what we want is to invite outstanding speakers in the broad landscape of computational science so that we can analyze the relevance of modeling in society in different aspects. As I said, the first one with Marianne, we focus on the role of really the effort made, in particular also by women, in the development of computation at the very beginning and the challenges at that time when this explosion couldn't be thought of. Today we will look into the interface or interaction between industry and modeling, and we will continue with bringing outstanding people in different aspects of modeling. And the idea then is also to have these events that can reach broader public, and that's why we organize it here in EPFL, and we open to the EPFL community, but we also stream it so that the community associated to Marble or the broad community of Cecam across Europe can also follow us remotely. And we decided to keep or to organize it in a format that is a bit different from the standard scientific presentations we are used to. We will have a first presentation by the invited person, but then in order to also go beyond the formal presentation, we thought it's very fruitful to have a second part that is more a conversation. So we, in this case, invited Bill Curtin here at EPFL, and who has strong background of also interaction with industry, to be able to discuss more informally, more personally, what are the views of Massimo in this case, and also then you as an audience can have this more open discussion to have a broader perspective into this subject. So I hope this is a fruitful event that is useful for you, that as Sarah said, we want this to be interactive, so at any time you can ask questions, and I hope we all learn better about this impact and looking ahead what are the future views or vision that our speaker will have in how this interaction can further develop. So in order to start with the event, now I pass back to Sarah to explain you the details of how we are going to organize ourselves today.
Thank you, Ignacio. Very rapidly, I hope. Here is a sketch of the program. We are going to start with a presentation that is going to last about half an hour by Massimo. And then this will be followed by 10 minutes of question and answers. I would ask you to focus your questions in this first round of questions on technical aspects that have been discussed during the presentation. There will be an opportunity to interact more informally and more broadly with Massimo later on, as you can see from the program, because the second half of this event today has two parts. The first one is this conversation that will be led by Bill and that will cover a set of questions that we have identified as potentially interesting for the audience and that we want to use as a starting point for further inputs and explorations from you and with you. And these again will probably last about half an hour, followed by a conversation with the public. We don't have a strict limit on times for this one, so a lot will depend on you, how long it's going to last, how lively it's going to be. Again, let me stress this once more because this is very important for us. We would like this to be a useful, informal, fun opportunity for all of you to explore perhaps a career path or perhaps ways of using simulations and ways of benefiting from what you have learned as scientists up to now in a broader environment. So please, please, please do take advantage of this. Just a few words of introduction for Massimo before he presents himself much better than I can do. Massimo has a background as a chemist. He graduated in Padua as a master's student, and this was followed by a PhD at the University of California, Los Angeles. And he completed his academic path thanks to a Marie Curie fellowship at the Amolf laboratories in Amsterdam, with Dan Frankel, I think, yes. Then, and this is the reason why we are so interested in having him here with us today, he pursued his scientific interests, which are mostly focused on modeling of complex fluids, in particular using mesoscale modeling, within research and developments in a large industrial conglomerate, Unilever, where he has spent about 17 years doing research with development of new products. More recently, and this is yet another very, very interesting aspect of his path, he has become, and this is going to be something that I need to read, but Director of Business Development for Science and Technology Facility Council, with the task of fostering transfer, technological transfer, of supercomputing tools within the realm of modeling to large or small industries. So he's going to tell us a bit about these experiences.
Thank you. I will.
And
Pleasure.
Massimo, you have the floor.
Oh,
Please
thank you
keep
very
an
much.
eye on me. I will give you a sign when you have
Right,
about 10
okay.
minutes.
Thanks very much, Sarah. Thank you, Sarah. Thank you, Ignacio. I'm honored to be here to open this series of presentations and conversations. So looking forward to sharing with you some of the computational techniques that I've used in my past research, but also the choices I've made throughout my career. So again, looking forward to the questions from Bill and also questions from you, from all of you. So I think it will be an exciting afternoon. But first of all, what am I doing now? So I work now for the Science and Technology Facilities Council, which is a science funding councils in the UK. So essentially, our job is to look after big facilities in the UK, which are so big that no single university or no single company won't have on their books. So for example, STFC manages a large supercomputing center, the Hadrian Center, manages a diamond, the light source, manages the neutron scattering. Again, these facilities are so big that no single university or no single company can actually afford to run them. So that's why there is a set of people, which is us, whose job it is not just to run them, but also to help scientists, whether they come from industry or from academia, to come, use the facilities, and we will hold their hands, put the test tube in here, press that button, and then come home with not just the data, but some results, some analysis, so that we understand why the sample was doing that. So that's the job of the Science and Technology Facilities Council. It's one of the 7 councils within the UK. There are other councils focusing on physics and engineering, or biology, or medical council. All of these work together within a new organization called UK Research and Innovations. But our specific job is to look after these big facilities. And so I'll tell you a little bit about that, but also as a preamble, I will also talk about self-assembling system. And this is what I've been doing in my past work at Unilever for a number of years. And this is all about looking at fluids, complex fluids, how they self-assemble into structures which are spherical or flat or long worms. And these are made of these molecules, which are surfactants. They're made of a head group, which loves water, and a tail, which hates water. So when you put them together, in fact, they self-assemble, they arrange in a way that actually, so that all the tails that hate water are on the inside, and all the head groups, which loves water, are on the outside. But I'll tell you a little bit more about that in a second. And that's where I work. So this is the Daresbury site of STFC. It's in the northwest of the UK, close to Manchester, Liverpool, facing Ireland. And you can immediately see the big tower there. That, in fact, used to be a Van de Graaff generator, a big belt going up and down and generating huge sparks. And with each huge spark, we actually crack the atom, essentially, and then use that to actually look at the effect within the first light source system, which was at Daresbury until probably the 90s, and then it was moved down south, close to Harwell. But a lot of the knowledge still in the area of accelerator science actually still resides there, and this is where we actually try new systems, new designs, and this proximity with the National Science Lab has actually made the site grow and attracted a number of companies on site as well, as I know is the case for this site as well. So if you look at this picture, for example, you would see that, say, on this side, mainly there are the STFC facilities, but on the other side of the road, there are buildings in here which are hosting a number of companies, big, medium, small. They want to be co-located with us because just the proximity and the dialogue really helps them with their businesses as well. So part of my job is to make sure that we have a healthy inflow of companies on campus, that we actually foster those collaboration and make sure that these companies increase their productivity and then work better just by being next to us and then collaborating with us. One of the specific buildings here on campus is this building here, which is the Hartree Center. The Hartree Center is perhaps unique in its being a supercomputing center. So it is probably the only one in the UK which is a supercomputing center with a specific mission to be interfacing with industry. Of course, there are others, but this one has a specific mission to do that. So the job of the Hardware Center is to try to translate the new classic computer simulations tools, also machine learning or data-driven tools, so that we can help the UK industry grow and prosper, and translating that into ways that industry can use to actually make new products faster and cheaper. By doing so, there are some staff on the books of the Hardware Center, which leverage, of course, all the other talent within SDFC more widely. For example, staff that are formally part of the scientific computing department based at Dasbury, but also somewhere else. But also collaborators, which are also co-located at the Hardware Center. So there is a number of researchers from IBM Research co-locating there as well. So, I mean, a big powerhouse of scientists that probably can speak 2 languages. They know how to do computer simulations of different types, atomistic, mesoscale, large scale, but also have the domain expertise. So they would know how to translate that into challenges that have to do with life science, biology, or physics, or chemistry. So therefore, when they interface, say, with a company, they will be able to translate the question, the need, into the domain language. Is it something to do with biology? How do I narrow down that problem? But also coming up with a code or a workflow, a series of codes that actually help solve that problem. So this kind of a double skills, duality in skills really helps making that translate what is probably kind of too hard for the end user, so that it becomes much easier to use at the end. So yeah, so that's what we do there in the Hardware Center. And typically, kind of why would companies want to come and talk to the Hardware Center? Well, for a number of reasons. Well, first of all, because of this domain specialism, and then be able to translate, as we just said, from a technical expertise to a computing knowledge that actually will deliver that solution. But also because by doing so, they could access this technology and then run the calculations faster and cheaper, and actually get to the end result, which is to launch a new product, again, in a much more effective way, maybe a better product as well. There are already some full-time scientists which are already on the books, and in fact, the company could actually make an arrangement through the Hardware Center so that a scientist is appointed to work on a short-time project or on a long-time project. So again, there is a flexibility which kind of matches the industrial timescales. And also, I think that in the end, I think that through these collaborations, the Hardware Center and in general SDFC is really becoming, for the companies that we work with, really being a trusted partner. And that kind of means that you just go from 1 or 2 projects into a pipeline of projects, and that kind of that really goes up through the hierarchy of the company, and then become really the go-to place where you want to go first if you have a problem that really, or a challenge that needs help from our side. But let me move forward and kind of, now that I've explained to you what I do now, some of the challenges that in fact I have learned through my previous career, specifically in the area of liquid formulation, but more specifically in the area of surfactant science. And then surfactants, which I said, are these molecules which self-assemble into shapes, spherical or long worms or sheets. I will tell you a little bit about which techniques one might want to actually use to address these questions. I'll go into that. And actually go quickly into some applications. So once you have the challenge, once you have chosen the right technique, what do you do with it? So which are the typical applications? So I'll tell you a few stories about how to calculate the phase behavior using these techniques, and also how to calculate things like the micellar properties, and I'll tell you all about that. But in the end, the work is not done if we don't make these techniques available and easy to use by the end user. Someone who's an industrial scientist who want to be able to do this in their own daily jobs. And this is kind of the extra step that we actually try to add every time. So what are the typical questions that a company, say, in the area of formulation might want to ask? So they will be formulating a liquid product. It could be a shampoo, it could be a liquid detergent, it could be a fabric conditioner. But key feature in there is, for example, the viscosity. So how much does it flow? Is it too thin? Is it too hard? If it's too hard, it wouldn't come out of the bottle. If it's too thin, it will pour out and do a mess everywhere. And you want it to be kind of in a state, in a structure, which is easy to dilute as well. So getting that structure, that mesostructure right, is absolutely key feature, both for the consumer perception of it, but also because of the functionality of it. But then the viscosity actually is linked to the building blocks of the material going forward. And this being kind of a liquid mesostructure, the building blocks of such a surfactant system are worms, essentially long micelles, maybe something like that. And then in fact, the longer the micelle, the higher the viscosity. So again, there is an easy understanding of what needs to be done in terms of creating the right mesostructure, because one can clearly link the length of these worm-like micelles to the macroscopic quantity, which is the overall viscosity or the density of that. And in fact, the question to be asked is, how do I regulate that? Can I come up with a way to actually do the computer simulation first, do the computer experiment first, and then it will guide my real experiment so that I can make that product? Another typical question that people might ask is, how do I predict cleaning properties? So how do I lift up from a surface an oil droplet? Something that could be on my shirt or something that could be on a hard surface. And that lifting up of that oil droplet is all about changing the interface between the oil and the water. And in fact, the way in which you change the surface tension at the interface is by using a surfactant, for example. If the surfactant, which is in fact in a micelle, will actually break up into small monomers, the monomers will flow at the interface, and then they would change their property and make this oil droplet more soluble. And then you can actually lift it and then clean away the dirt. So these are typical questions. And then, in fact, you might be surprised that, in fact, the cleaning power of a formulation actually relates strongly to how quickly you can make that micelle, you can break off that micelle. So knowing something about the critical micelle concentration, which is a hard experimental piece of data, can tell you something about the macroscopic behavior of the cleaning power of, say, of a certain formulation. So how do we deal with that? I'll answer that in a second. But in the end, again, wouldn't it be nice to be able to create a tool, to create like a computer version of the real experiment, and then deliver that to an iPhone or to an iPad, and be able to do the virtual experiment in a way that, so simply that, in fact, I can hand it out to one of my colleagues, to one of my ex-colleagues or new colleagues down the hall whose job is to create a new material, new formulation, and then try out. And then help with the thinking process by trying different things first on the computer, and then, of course, do the real experiment, because you have to do that. So one of the approaches could be to go for a classic simulation, do like a molecular dynamics type of simulation, where you look at the molecule in its full glory details. So where you can detect and then really look at the position of all the atoms in the chain each second, or each millisecond, or each picosecond. Well, that's great. But then, in fact, really, if you really wanted to go to a big system, you couldn't possibly do that. Well, first of all, because I think that if you are really looking at that level of detail, even with the most powerful supercomputer on Earth, you cannot go to long time scales. And really, perhaps you can go to maybe 1 millionth of a second, maybe more, if you really want to look at the molecule in that level of detail. And not really much happens if you have a micelle within a millionth of a second. It hardly moves. So again, one might want to sacrifice that level of detail and come up with a scheme which is a coarse-grained scheme, where we make some approximations and we say, well, actually, let me think of this molecule as a chunk of blobs. And each blob, of course, will make chemical sense. So maybe one blob could be representing a bit of the CH2 down the chain, or one blob could be representing the benzene ring, or one blob could be representing a carboxylate group. And if I string them all together, then I have a model. Of course, it's not the real thing. And of course, I sacrifice the knowledge of what happens within that blob. Then the advantage is that by going to this mesoscale, intermediate scale, then of course I can go to much bigger chains, and I can have much more molecules within my field of view, so then indeed I can possibly look at not just one micelle, but I can look at many micelles within the simulation time. And in fact, even more interesting, one can go to real time of milliseconds to seconds. And that's interesting, actually, because if you're asking a question which is relevant to, say, how this formulation interacts with the consumer using it, so for example, you will start washing your hands, and you can see the micelle formation within seconds. Or when you walk into a shower, again, you can see this happening within seconds. So you start to access timescales which are relevant and important for the question that you're asking, which is relevant for. So that's one approach which we have embraced in this to ask specifically those questions. This is the questions of self-assembly and the question of phase behavior, phase change. So there are many ways in which one can actually look at the mesoscale. There are many techniques out there, and I'm sure the experts at Cecam know all the secrets of it. We have gone for one, maybe for historical reasons, also because of choices on the technique, which is actually quite good, was good for us, at that time being. And this is dissipative particle dynamics. It is a particle-based techniques where all these particles move around according to Newton's equations of motion. You can track the position and the velocities of each of the particles, and the particles interact three ways: through conservative forces, which are pairwise, and they are soft. So these particles can go through each other and actually get to equilibrium faster. Drag forces, so you actually increase some kind of viscosity in there, but also you have to put some energy back into the system through some pairwise random forces. Now, there is a special choice here of the random forces, which are pairwise, and also which intensity is linked to the intensity of the drag forces. And that specific choice, in fact, preserves momentum. So in fact, in the end, and I'm sure that Ignacio is an expert on this, you can prove that this actually preserves hydrodynamics in the system. And that's something that you want to have. If you're asking the question of self-assembly, you want to make sure that your system behaves as it should behave in the real world. And that's one of the reasons why we have gone for that. Of course, there are some limitations, and there are other things that one could actually use. But that's, of all this slide, if you have to remember one thing, please remember this, that all the interactions between blob A and blob B, if you boil it down, is down to one number, that number A, which tells you how much this blob likes that blob, or this blob doesn't like that blob. And all the detailed interactions, so van der Waals interactions, dipole-dipole interactions, you name it, they all come back to one number, the A number, which is essentially maps onto the excess free energy of interaction between this guy and that guy. So in fact, this seems to be quite artificial to look into blobs, but in fact, this actually maps onto hard thermodynamics, because then if there is the thermodynamics of mixing and demixing at that particle level, blob level, then of course you automatically ensure that the thermodynamics of the macroscopic model should be right. And that's exactly what we're counting on. So, example, application. So this is all good and well in theory, but in practice, does it work? The answer is yes, of course, for the system that we've looked at. So this is a typical surfactant that many companies use in the area of surfactant science. It's called C12E6 because there's 12 carbons in that chain and 6 EO ethylene oxide members in the head group. So that's what you see if you look at the level of the chemistry within that molecule. But in fact, you can start to coarse grain it up. You can blob it up so that you can think of the chain as blue blobs. Each blob will be CH2, 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 and then you have a number of those. And the same thing for the head group, the red guys, the red blobs. And these are the ones that love water. So again, we have drastically simplified that. And now, well, in fact, we should say that we have coarse-grained water too. Now that we have actually coarse-grained that, then the game becomes a lot simpler when it comes to running the simulation, because then you don't need to keep track of different types of atoms. We only have blue blobs, red blobs, and gray blobs. So we just have to find the right excess free energy of interaction between red and blue, or red and gray, blue and gray, and then thanks to that, we can set up the simulation, move these particles around using Newton's equation of motion, and then in fact, see if that system self-assembles into the right shapes. Of course, you want to test it first. And one of the tests could be done, for example, on a surfactant of which you know already what the phase diagram is. And this is the kind of the map, the formulation map for C12V6 in water. If you look at the graph here, so you would plot the concentration of C12V6 going from 0 all the way to 100%. So this is 100% C12V6. That's 100% water. And of course, there's temperature on the y-axis. This tells us that if there is not much C12V6 around, surfactant around, then you might want to self-assemble into spherical objects, spheres. If you have a bit more, kind of 50-50 with water, then you start to self-assemble into long objects. These are cylinders, and these cylinders actually pack in a hexagonal way, if you look at it from the side. But if you have even more, then you go into the lamellar space, which is a phase where you have slabs of these surfactant structures, and they pack one on top of each other. So depending on the concentration, you would have 3 different types of structures, which is very interesting at the mesoscopic way. But then macroscopically, well, we know that this stuff flows really well, pass through each other really easily. But if you're stuck in something like that, it wouldn't come out of the bottle. So again, I mean, if we already know what the surfactant map looks like for a surfactant, then we know what to do and what to avoid if you want to regulate that kind of a viscosity. But if we don't know that map, right, and then we wanted to start a series of experiments or a series of formulation, then, of course, you would want to build that map first. But building that map, point by point, experiment by experiment, takes a long time. Weeks, maybe months, if you want to be very precise. So one alternative could be, can I do that on a computer first, if I have the techniques to actually build up that map? And this is exactly what we've tried to achieve. But let me tell you what is the kind of I mean, I always love this, the old school way of looking at the phase diagram. And that's kind of called the penetration scanner. Some of my old colleagues in Unilever still do that sometimes. So you take a glass slide, and then you put a drop of water on one side, you put a drop of surfactant 100% on the other side, you cover it up with a glass slide, turn it over, and look at it through cross-polarized light. Cross-polarized light means that you will actually pick up features, if there are any features. So if something is completely homogeneous, you see black. And when you see features, you see some kind of light things in there. So you could guess that, of course, in this side, then you would have a completely isotropic system. That's the micellar system, spherical. All the way to, oh, now we have some features. Now some streams. That's the signature of these long columns, long tubes. Over to these, called the Maltese crosses, where you have like a birefringent system, again, and this is the signature of the lamellar phase, all the way to another black here, which is the inverted micellar phase, which is exactly as the micellar, but the other way around. And by the way, if you're asking, this thing in here is isotropic because it's an air bubble, which was trapped in there. So that's what you can do, I mean, old school on a glass slide, and again, and this is very fiddly, but it gets things done because you know where the phase boundaries are. And of course, one can do all the assignments and know exactly which phase is where. But the other thing to do it is to try and do this on a computer. So using the same methodology, so we blobbed up that surfactant, we blobbed up the water, and now we can actually put this artificially on a glass tube, which is our simulation box. On one side, you can fill it up with water, yellow, and on the other side, you can fill it up with surfactant, green. And then you lift up a magic partition and let the two things mix. So water will swim happily in that direction, and the surfactant will swim happily in the other direction. And really within real-time simulation, probably 40 minutes, 30, 40 minutes, you start to develop this at the interface. Let me just pause this for a second. Right, oh, no, what did I do? Let me try again. Yeah, okay, let me do it again. need help. Ah, okay. Oh, I didn't see it in here. Okay. Oh, right. There you go. Thank you.
Shall I leave you?
Yeah, no, okay, thank you. So if I click that, out again, there you go. So within a matter of minutes, really, then you will see the phases actually developing. And if you insist that there is a concentration gradient, so on this side, pure water insisted there, on the other side, pure surfactant, then there is a formation of the micellar phase, spheres, the columns in there, and if you can look at it from the other side, then you would see the slant, one hexagon, one column with 6 around, then the layers in there. So again, one can actually develop that map and go back to pinning down those phase boundaries within a matter of minutes. Again, you can do that at one temperature, or you can move the temperature up and down and actually develop all those features. Let me focus now on one thing, which is these micelles in here. So again, the other question that we can ask is how do I develop those micelles? And one can look at the interface and then the formation of micelles, which we've published recently in collaboration with IBM, one of our co-partners. Key is, of course, to get all the parameters right. So the how much blue like blue, how much like red. So one way to do that is to make a connection directly with real-world experiments. And we've chosen to do that by connecting directly to solubility data. So we looked at a parameter called the log POW, which tells you how much a same solid can go into either the oil system or the water system. And of course, we've used existing data to benchmark that, in fact, our parameters were actually right. And we fitted with those parameters to unknown, and we actually got a pretty good result. So that is one of the ways which we can make a connection within that. You also have another movie here. See if I can actually make that work. So this is what would typically happen if you run a computer simulation of a surfactant in water. The gray here are the surfactants. The water is transparent, white, and then the blue are the counter ions. So again, here perhaps you can see that these surfactants might want to self-assemble into spheres or almost spheres. Of course, they break and then they reform. It's a very dynamic situation. But in fact, of course, movies are nice, but then we want to extract as much information as possible from that. So what you could extract is start to asking the question, what is the probability of finding a single surfactant system in there, a single surfactant monomer? What is the probability of finding 2 of them together, or 3 or 4? And plot that probability, the distribution, as a function of the aggregate number. So 2 things you can get from that diagram right away. One is what is the most likely shape that I get? And that's, of course, the height of that peak, which is the most probable aggregation number, and that is the size of the micelle. But the other thing, which is even more interesting, is the blue bit, which is the area under the curve, starting from 1 all the way to the bottom of that curve. And that is, by definition, the amount of surfactant which is in equilibrium with the micelle state. So by definition, that is the critical micelle concentration, how much surfactant you have to put in before you form a micelle. And that number that links directly with the cleaning power, as we said before. So again, simple simulation, nice video, but then we can extract a lot of information from that and getting useful numbers so that our collaborators down the hall can actually use them to devise a new formulation that cleans better. The other thing I wanted to mention is the fact that you could look at more systematically into the length of these micelles, and you can make a correlation between that length with the length which is observed into like a micrograph. And even more interestingly, you can start to mix in many more ingredients. So this is an example of 3, water, oil, and a surfactant. So not just in looking at that, how to lift things up, but then again, you start developing like a map of 3 systems, 3 surfactants, or 4 surfactants, or even more. So again, since real formulations are very complicated, you may want to start to look at ways in which you can cut and then simplify this in a way that can actually help. And in fact, for example, here we can already look at, for example, the area of stability of micelles, which is over here, L1, of these columns, which is the area of stability there, H1, or 2, which is the mixing between oil and water. And all the points which are within that dome will actually spontaneously be mixing into like an oil-rich and then a water-rich phase. The other example I wanted to show before concluding, Sarah, is really what happens in the high concentration regime. And this again applies to, for example, the oil sector, which is again, the type of companies that we tend to work with at SDFC. So there are challenges, for example, how do I make my oil so that in terms of a filter, when I have to start my car in a very cold weather, I don't actually clog the filter with wax. So of course, this is all about packing these long chains into something which may become waxy. So of course, the answer to that is, how can I blend it with something shorter? Shorter chains, more mobiles, will actually decrease the level of order. So if the green is representing the long chains, very ordered and making the wax, gray is the shorter chains, not order. So the question is, where do I stop? And again, you could do, in principle, a number of simulations that will tell you where exactly will be the right ballpark, and then again guide the experiments afterwards once you are within that ballpark. And again, in the end, of course, once I've developed all these tools, of course, the ideal would be to make it available to the collaborators down the hall who actually are doing the experiment. And then they may not be interested in how to submit the job using Linux command lines, or they may not be interested in knowing what a parameter actually means. They would want to know, how can I use this to help me guide my experiment in a much more effective way, and then try things out before I actually do them for real. So we've done that as well. So again, this is just a prototype of an experiment that we have done across the organizations, Unilever, IBM, and the Hartree Center within SDFC to develop a very simple interface. Really, the same penetration scan simulation that I showed you before can actually be implemented as a simple interface on an iPad. And then here, really, the user could move the finger up and down and then dial up the temperature or dial up the different types of surfactants and actually have a first glance of what the different phases are if I change this. And again, this would be something that would be cutting down on innovation times dramatically, because if you want to try something new and you want to try something, say, a new surfactant with 7 or 8 or 3 or 4 different groups, you would have to phone up the supplier, wait for a few weeks for it to come back, and maybe it's the wrong one, so phone again. So again, this is a way to actually try this out in a way so that you know exactly what you want. And then, of course, you have to do the experiment with what you have. So let me stop there. Let me put up just the last slide, which summarize what we actually talked so far. So we started off with which are the typical challenges in formulation science, especially in surfactant science. We talked about mesoscale technique as one technique that one could use to ask the phase diagram questions, or the micellar question, or kind of the deformation of that mesostructure. So I showed you some examples of how one can apply that, either for the phase behavior, where they have the phase boundary, and also to talk about the micelles, because the length of the micelles and then how quickly they form links to things like, for example, the degree of detergency, and how you can actually mix that, of course, with other ingredients. So we talked about oil, but there could be others as well. And also, of course, how do we deploy that to end users within all the ifs and buts that actually have to be said about that. So with this, let me thank you for the attention and looking forward to your questions.
Thank you very much, Massimo, for this interesting presentation. We have time for a few questions on the presentation, so who wants to start?
Well, that's very beautiful work. Of course, we all know the devil is in the detail.
Of course.
And specifically in the force field.
Yeah.
Any words of wisdom? Because what the customer will ask, not only what is the answer and what is the error bar?
Yeah, of course, yes. So the devil is in the detail, and of course, there's two ways to optimize the force field. So one could use like a top-down approach, and one could use a bottom-up approach. The choice here, has been to use a top-down approach. So link those mesoscale property directly to experiment. The alternative is to go bottom-up. So to start from like a molecular simulation and coarse grain that, and then use that as the benchmarking for the mesoscale simulation. Now, I personally don't like that, because even the atomistic simulation is a simulation, so you would be benchmarking a model against the model. So the approach here has been try to go directly and link to experiment, because it gives us the best chances of actually getting that right. And of course, to your question is what's good and what's good enough. So this is, a crude approximation. So we don't have real molecules in there. In this mesoscale approach, we have balls, strings. So I would be very happy if that approach gives me kind of 80% of the answer. And that's probably what we get. So do we pinpoint with that approach down these phase boundaries to a high degree of accuracy? No. Do we get the right trends? Yes. So I think that is actually kind of a most valuable, because then, in fact, I think that the best way of using techniques like this, especially in the mesoscale area, is to look for trends, to look for order, and to look for ideas that, in fact, helps trigger what is the real experiment going to do. So, in fact, if we can point with such an approach to the right direction, is it more salt or less salt? Is it 5% or 10%? That really is a good, and of course, you have to do the real experiment. That is the reality, right? So this only helps, I guess, narrow down the space of possibility. Because, I know how things work in industry. So you will start from a comfort zone and say, well, that's where I know things work. So let me try and change plus 5%, minus 5%, this way or the other. So sometimes you do actually stay within the comfort zone. So having a technique like this would allow to, at least in principle, well, look at all space of possibilities, which otherwise you wouldn't look at. And then perhaps identify areas that are potential good hits. And then, of course, zoom in. And then perhaps now do 5 experiments in these areas which are actually more promising. But you're right. The devil is in the details. So again, so the force field that we wanted to look at is something which has been optimized for a series of surfactants and polymers which have those groups. If you fall outside that, of course, this is the range of validity. And then you shouldn't be asking that question.
Thank you, Massimo. More questions? One over there.
Hi, thanks for the talk. I was just asking, how did you incorporate the temperature thing in your model? Because I see that you are making these globs of. So how do you choose a glob size, and then how? So you're doing this homogenization, but you are also incorporating temperature. So how do you incorporate dynamics in the globs and in between the globs? So where does this come from?
Right. So each blob is chosen just based on the structure, and then we have kind of one makes choices about how big you want the blob to be. In this particular case, we went through kind of a rule which is about 4 to 1. So 4 real atoms to 1 blob. And we decided to actually keep the same volume more or less for all the blobs, for consistency, right? Which actually helps with keeping the density the same. Then these blobs interact through some local interactions. So you set the pair potential. You don't set the temperature. So the temperature is set through the simulation. So through those 3 forces that I showed you before, then actually the balance between the dissipation and then random forces sets the temperature. And then you can set the temperature that way, as you would do in any molecular simulation. So you set the temperature through the balance between the random forces and the dissipation forces. The results that were on the board before, so they were all calculated at the same temperature, which is room temperature. Why? Well, because that's room temperature. And also because it's actually temperature where kind of most people would want to look at, especially if you're looking into formulation science or surfactants. You would use them more or less at room temperature. But in fact, the same parameters we've checked would be actually valid within a range of temperatures, probably between 50, 60 degrees down to 10 degrees. Again, with no additional changes, the same numbers which are calculated there are also valid in there. In terms of getting trends, or because they would work. If you are far outside that, of course, you would have to reparameterize it. But then again, that gives you kind of a pretty decent width within, obviously. So you don't have to change parameters if you're within that band.
We have one more question over there.
You have to wait for the silent microphone. Camera.
How mature is this process? Like, are there actual products that you say wouldn't have been developed without computer modeling, or is it still more theoretical?
Yeah. So yes, there are. So again, I mean, it's pleasing to see that in fact, company I worked for, in fact, has used this in the past to actually help guide the selection of some of the products. So in fact, I think we have a slide later on that actually says, well, it may have been on the critical path, may have not been, but in fact, these simulations helped really point in the right direction for typical liquid products. So I can think of a number, which I'm not allowed to say, but then in fact, they have been used quite in anger. And again, not just by the company that I'm very familiar with, but many other companies play a very similar game.
So if you work together with a company and then you develop the workflow and a new technique for whatever for 3 months, so they paid you for that, I guess?
Yeah, well, I mean, it depends on the type of relationship or type of agreement that you may want to set up. And I'm sure that they will touch on that, Bill, I mean, in the discussion later on. So of course, as a research institute, we will want to collaborate with different companies, big, medium, small, and of course, depending on what they need, we will be able to come to an agreement of how we can help them. So some companies come to the Harvard Center, and then they already know what they do. They just need to scale up and then use the computing power. And again, there are mechanisms for doing that. So in that case, the fact that people are actually very good at translating that software or perhaps installing that and tweaking it to the machines we have. That's what we can help with. Or sometimes a company would want to develop together a new technique. And in that case, well, if it's jointly developed, then we have to come to an agreement of who owns what. And then, or some other time, a company would come and say, well, I know that you have a tool that may actually be helping us. Why don't you run your own tool for our own applications? So who owns what? It depends on what type of contract or what kind of agreement is actually put in place. But there are several models, of course.
Okay, so as I said, there is a question from the director. I don't think I can skip that
nice.
one.
Coming back probably to the first question by Eric. So there is, in the use of these mesoscopic models, how much you have focused on how you use this top-down to identify phase behavior. When you now move on to look at the general mechanical properties and the non-equilibrium response or the viscosity that you referred to which extent you can also keep that the same approach, or you can ensure that it translates to viscosity, whatever you know for the phase diagrams?
So we've never calculated viscosity. So we've calculated, proxies of viscosity, as in length of the micelles and degree of entanglement or number of branch points, which we take as proxies for learning how the viscosity will change. In terms of trusting the non-equilibrium behavior, I wouldn't trust it. And you know better than I do that, in fact, work needs to be done on these techniques to actually go from the thermodynamic questions to the out of equilibrium question. I think that probably the best value for a technique like DPD are really the thermodynamic type of questions. And this is what actually works, because it kind of rests on looking at the excess free energy of mixing. Anything which is out of equilibrium, I think, is still very much in the development phase, and it's something that I know Cecam is working on.
Okay, well, thank you very much for these questions and answers. I would like now to move to the next part of this meeting, and then I would like to invite Bill, Curtin, and Massimo to make themselves comfortable on those bright red armchairs that we have prepared for them. As they do that, let me just present, for those of you who do not know him, Professor Bill Curtin, who is currently a professor of mechanical engineering here at EPFL. Bill has a background as a physicist. He got his PhD in physics at Cornell. And then, interestingly, he had sort of an inverse career path compared to the one that we have just described for Massimo, because his first job experience was in the private sector, and he was a research scientist with British Petroleum for a few years. Then he decided to leave industry and come back to academia, and he held faculty positions at various American universities, most notably and for the longest period of time at Brown University, before coming to EPFL in 2011 to take on the role of director of the Institute for Mechanical Engineering here. As you will discover, Bill is a great person for conversations. That's one of the reasons why we asked him to be here. No pressure whatsoever. Oh, sorry. No pressure, as I said.
Right.
But we've also thought that he was the right person to have a chat with Massimo because of his experience in industry, both as a researcher and because throughout his career, notably at Brown, he has been responsible for establishing long-term collaborations with the private sector. Also, Bill is one of the PIs in Marvel, and within Marvel, he is responsible for technology transfer processes. So with these brief words of introduction, I think that I am now going to just leave the stage to these two gentlemen for a first part of the conversation. Thank you.
Good, thanks very much. So, a conversation of sorts. My thinking is many of you may end up working in industry, so one of the advantages of having someone like Massimo here is to gain some insights into what many of you might experience in the near future or the moderate future, or maybe in the long term. So we'll start out with some questions along those lines, just to get that perspective, because we have many scientists, mostly academics, come to EPFL and give talks. Rarely we have industry people, and rarely do we have the opportunity to have this kind of a discussion along these kind of lines. So, you finished your postdoc in Amsterdam. You were doing real, hard physical chemistry, then in Amsterdam, and then you moved to industry. And so, when you started industry, were there aspects that you'd not expected? Like you had some vision of what it was going to be like, and something was quite different.
Well, some of it. I knew that moving to industry would have been kind of dealing with real problems, messy problems. I knew that kind of a move to industry probably would have been pressure on timescales, kind of working on something, but not to be able to deliver to the 100%, to that level of details, kind of being happy with kind of ballpark numbers. So this is what probably, I was expecting. What I was not expecting is that, in fact, since probably day one or day two, I discovered in the research center in Port Sunlight with Unilever, I discovered a high level of collaboration, especially between my role, as a computational chemist there, and my colleagues down the hall doing the real experiment. To the point that in fact, many of the projects, of course, as you know, are kind of are mixed teams. Are run by mixed teams where there is one theoretical person or one simulator, one experimentalist, someone who knows about finance, someone who knows. Yeah, so it's very much mixed, but they're all driving towards the same goal, and then the goal is to make a new invention, to find something new, either a new molecule or a new formulation or a new ratio, which works. So working to very tight timescales, and then being able to implement it, make recommendations, make it, and also put it on the shelves, especially in the sector which is kind of which is named fast-moving consumer goods. So speed is the essence there. And I say collaboration because again, by all the team going towards that goal, you would want to try things out, and then put aside your own kind of a personal workhorses or personal preferences. So more than once, in fact, the colleague down the hall would say, well, I've got this challenge with this formulation. I'm not quite sure whether I should increase the level of salt. So could you do a quick calculation for me? Of course. So you do that kind of a ballpark calculation, which may not be perfect, but they give you trends, and again, and then they would try it today or tomorrow, and then if it doesn't work, they would come back to you and say, oh, actually, I tried that, but in fact, the model may not be right, because so then you do it again. So that level of very fast turnaround of trying things out, and then high collaboration is something that, again, I mean, I had not experienced before.
Would you be refining the model then if they come back and say, I tried it and I got something different? Is there enough turnaround time for that?
Well, if you're doing pencil and paper model, yes. Again,
pencil and paper.
Pencil and paper you can, of course, not in a simulation, but then if the model is as simple as writing down kind of, a free energy for a system, then you can add one extra term and then do the calculation again. So if that is the case, then you can do it and try it again. If it is a simulation, no, it's a bit more time consuming. That, yeah.
So you weren't expecting this
I wasn't
level of
expecting that.
collaboration?
No, I wasn't. I wasn't. And in fact, probably, I mean, again, kind of thinking back, perhaps it is just because kind of the team works very, very tightly, typically, and again, and in a manner which needs to deliver within short time scales. So that kind of a high level of interaction and kind of going back and forth is something that I personally did not expect, and then I was very, very surprised to find it.
And so related to the team, so would you be the only theoretical person working? Did you have colleagues who had the same theoretical chemistry background?
Yeah, I mean, my background again is computational chemistry, as you know, and then I've done also a little bit of theoretical chemistry, so both computation, but also kind of a pencil and paper type theory. And yes, I mean, I probably would be the only one within the team with those skills. And again, if you think about how the team works, then there is one theoretical / computational person. There is one or two experimentalists whose charge is to actually try things out and then develop the new formulation. There would be one person who's thinking about supply chain already. There will be one person who's thinking about regulatory aspects, and that means is this molecule something which is allowed? Is this molecule something which is potentially like an irritant? Again, I mean, even at a very early stage, when you're looking for a new molecule or a new formulation, you want to know already, have a line of sight of what might happen down the road, because you don't want to do a lot of work on something which doesn't have legs. If what you're looking for is something which is too expensive to procure, it would never be an option. If what you're working on is something which has the potential, at least very, very potential of being like an irritant, then you wouldn't want to go down that path. So you want to be guided already by something which may be happening down the hall. And as you say, so perhaps being the only theoretical / simulation person, you often have to describe concepts which other people have never heard. So things like free energy. What's the free energy? I mean, if your background is supply chain of finance.
How many people know what the free energy is? A good crowd here. So
a good crowd, yeah. But if you're training finance, you have no idea what that means.
Free energy? We like that. We like that, free energy. Can we get more?
Exactly. So again, it's down to kind of, and I think that probably one of the skills, again, that probably you develop in those situations is to try to explain complex things in a simple way. And I think that is very kind of a good training ground for that. Kind of again, because you have to kind of break down those barriers of communication and then try to take that into a language or into an expression which everybody can understand.
Yeah, particularly if you're the only.
Particularly if you're the only one,
theory person. Yeah. So structurally, this will deviate a little bit from questions we planned, but structurally,
okay.
You would be in a group, or would the groups, like, how much dynamics is there in terms of you'd form groups to solve problems and then form other groups to solve the next problem that comes along, or would you be in a group that stayed sort of cohesive?
Yeah, so again, I mean, I can tell you about my own experience, but I think this is similar to other, companies situation, as well. So there would be groups that gather individuals with similar skills and interests. So there would be what is typically called like a corporate research group or the background research group, whose job it is to be the expert in that kind of area, domain. So look for the new simulation techniques or embed into the organization the new simulation techniques. develop and then work together with with academics and research centers the new version of it. Or there could be more, applied teams. So people or individuals who are charged with coming up with the new class of shampoos, or the new class of oils, or the new class of products to clean your home. So the role will be slightly different depending on where you are in the innovation funnel. And then from those groups, or there would be the finance support group. From those groups, then project teams are formed. So typically, anyone, at one time would be working on two, three things at the same time. So you would be placed into like a mixed team. That would be your project team with a designated project leader, whose job is to actually make sure that you deliver to certain timescales, but then drawing on your own expertise. So you wouldn't be working on that 100% of your time. There will be perhaps 1/3 of your effort, because then the other third will be on something else, and a third on something else. So you'd be part of these teams, and then when the project is delivered or come to a certain milestone, then the group dissolves, because that result is passed on to someone else. And of course, you know that within the innovation funnel, then you go from ideas to something more applied, to more applied. So then it is not the job anymore of the research establishments to come up with a new molecule. You hand it over to someone whose job it is to do the development of that formulation or do the optimization. So once the job is done, the project team is released, and then you start again on something new. Does that answer your question?
Yeah. So these projects, what kind of time frame might, if there was something that was typical, where you're talking a couple of months, which is like zero time on an academic scale, or a year, or anything characteristic? Yeah,
it depends is the answer. It depends on where you are in that funnel. Yeah. So again, I started to describe that, as a funnel. So I would say on the left-hand side, this is what you would, funnel, left-hand side is what you would describe as the kind of a more, the ideas generation phase. So this is kind of a more like blue sky research, or trying to come up with something very risky and very new, dislocating, kind of changing things dramatically. And you expect, a lot of these things perhaps fail, right? Because they wouldn't actually help. But then as you move closer to the other end, which is kind of towards the launch. So you go from ideas to research, to development, to scale up, to manufacturing, to launch. As you move down that scale, then the times become a lot quicker. So if on this side, the ideas phase, you would have perhaps longer time scales. And longer means year, over a year, 2 years, 3 years maximum, I would say. As you go down the funnel, then things need to happen a lot more quickly. So the projects will be a lot more shorter. And then the type of work also changes as well. So again, if you're on this side, say, so the job is to come up with something drastically new, high risk, but then there are some decision points where you have to go from, now that I have 10 options, which are the 3 options which are the best ones. So you only take those forward, and then so on and so forth. So the more you go down, I guess, the more you become low risk, because you don't want to change things too much, and it becomes more like an optimization project rather than kind of exploring new things.
So in the funnel, are the people doing the longer term high risk, do they follow something through, or does it get passed off that there are certain people who do, who are more inclined to do the high risk, and people who are more inclined to do the development?
More of the latter. I would say more of the latter.
So it's a little more structured. You could be at some place in the funnel.
You could be at some place in the funnel. But of course, I guess that the ideal would be to provide some continuity. So not just throw something over the fence to someone else and then catch it, but kind of try to provide even personal continuity. But then someone who's good at doing some basic research, who enjoy doing that, may not be so good at doing some manufacturing work, because they may not be enjoying that. But kind of a little sense of continuity through these gates, I think that probably is the ideal scenario, isn't it? So that you provide that even with the person. But typically, I would say that kind of pretty much, on average, then if your role or what you enjoy doing is with a certain kind of area, that's pretty much where your projects will be. Yeah.
And in your lab, then, how would the relative number of people, let's just roughly say, in these different regions of the funnel? Because the high-risk stuff, presumably, there are fewer people doing that. But
Yeah.
but I
I
don't
mean,
know.
I would say, well, I mean, I don't know about people, but what I can
Or
say
a
is,
percentage of effort or
Yeah.
research funding going to the different sections.
well,
yeah.
if you talk about the cost of the research, probably it's actually more costly as you go closer and closer to launch, because changing things in a formulation on a computer doesn't cost much. You can just, you run it for a few more hours. It doesn't actually. But actually, if you're much closer to the end, then changing the formulation there means doing another plant trial, for example.
Yeah.
Means cleaning the whole thing out and then trying something new. So that becomes very much expensive there. So in terms of the cost of a change, that is where it is. But the other thing that again, I mean, in my experience, typically happens is that there is a lot more interaction with universities and research centers if you are at the beginning of the funnel, because that place really kind of would you have all the experience and knowledge in house? Likely not to. So then that is the fertile ground to actually start new collaborations and then kind of work with the experts in that particular field, whether it is computer simulation or whether it is I don't know, oil systems, or whether it is perforation, if it's in, or anything else. So there you would look for collaborations. Again, and timescales then would be compatible with the collaboration. As you move further down, I think still that there are good collaborations going on, but they would be much more focused. So probably would be more like a consultancy, or calling in an expert to actually advise on one particular change, or what if, I would do that. So I think that again, the interaction with potential partners would be, of different timescales as well. And
So-
probably more intense on this end and then
Yeah.
less intense on that end.
So on this fatter end, which is always closer to the academic
Yeah.
side of things, so Unilever was open or involved with collaborating, maybe let's say with academics and not with other companies, but of course because you're competing, but with universities or
Very
bringing
good
in
question that.
bringing in people.
So I think that again, for the time that I've been there, and I've seen that with the company I was with, but also seen it with many of the other companies. I've seen a change between what was like the old model called the closed innovation into what is now termed as open innovation. So closed innovation again, and I saw that many years ago, but I've seen it also in other companies. So you would look for answers and then effort in-house only, being very protective about what you do, very secretive about what you do, trying to limit as much as possible communication with the outside world. And that model, people have seen, is not viable, especially if you need to turn around innovation at a fast pace. Because sometimes you don't have all the skills in-house. Sometimes you don't have everybody that you actually need to on your books. So that's why many companies have embraced what is called open innovation. And that means to collaborate more openly with universities, with research centers, but with also other companies as well. And there are examples of companies pairing up, big to big or big to small or small to small, where kind of you share the risk, you become more open and transparent. The advantage is that you actually get stuff done more quickly and perhaps with the right talent. So you get to a much better answer by trusting that. And I think that works really if you can set up that level of trust between your entity and then the other partner. If that trust is built on successes, is built on previous experience, and we have many examples of that, again, in what I've seen within my company, what I worked for, or also in other companies as well. So you develop that. But I think it was just going from close to open innovation. Of course, the trick is when you work with another company, how do you decide who owns
Right.
what?
Who owns
and in fact, we already had a question about that. It is who owns what? If you have that kind of partnership. And again, depending on the case, you can draw the line in the sand what you're both comfortable with. So, of course, it should be a win-win situation. It shouldn't be one wins all. There should be some kind of a, not a compromise, but a situation in which I'm happy and you're happy as well. And again, I mean, it can be different in different cases. So
I suppose there's a risk there's a cost, there's a benefit, there's a risk. So you
Correct.
take the risk of losing what you put
Yeah,
in, you take the risk of sharing the benefits,
Correct.
and everybody calculates
And in fact,
where they're comfortable.
if the, I mean, if the company in question is interested only in the applications and not the models, then that's it. So this is where the line should be drawn. I mean, if for example, company X and university Y work together and then say, well, now university says, I want to own the model, and company X says, well, I don't want to own the model, I want to own the application in my field, then the choice is done. Of course, we have to come to that kind of a level of balance, and if both parties are happy, that's great. If they're not happy, then there needs to be a discussion. And then for different companies, different sectors, that line can be drawn at different places.
Sure.
So depending on what actually makes sense for both parties. But I've seen a lot more of that going on. And in fact, I mean, now that I'm at the other side of the fence, I can probably see that, I mean, how it works in different sectors. If before I was only looking into surfactants and soaps and shampoos, which I loved, but there's more to life than that. So now I can kind of see how that applies to other companies as well, who are not making shampoos, but are making, for example, cars or airplanes, which is very exciting, by the way.
So do you see you're in the UK.
Yeah.
Do you see open innovation happening worldwide in the US and Europe in addition to the UK?
Many multinationals, I mean, across the world, I mean, are embracing that. I mean, I can see that across the board, both in the formulation sector and in the other sectors as well. In the US, there are many examples, I mean, of companies doing that.
Okay. So does that mean the companies end up doing more research, or collective? I mean, in terms of because they have to have people to interact. Do they take on more risky things because they don't have to absorb all the cost?
Well, it's still costly because
they don't absorb all the costs.
Yeah. So I think that I don't know if it's more or less, but what I think that is happening through that is actually the quality is actually going up quite a bit because the talent pool, I mean, expands dramatically.
Well,
there may already be, I mean, a solution out there which is not being matched with the problem again, which could be, I mean, a faster one. But I think that the quality of the outcome is actually getting, I mean, a lot better.
Okay. Yeah, it's interesting. I used to joke some years ago that you work with some company and they think the periodic table is confidential. So, okay, no, no, we know where the atoms are, right? And so the open innovation is a very sort of welcome development. It's a little bit maybe like crowdsourcing too, right? You just open up to more people coming in.
But of course there are risks, of course. But then if the risks, I mean, are justified, and in fact, if there is benefit for both parties, why not?
Yeah, so people are opening the way they look at what constitutes competition.
And again, I mean, and I guess that, I mean, in the end, from either way, you can protect yourselves with a contract. But a contract only, I mean, is worth kind of the people who actually write it. I think that really it's down to building the level of trust.
Yeah.
If you work with a trusted partner, then you know that your counterpart will be working with you towards the same goal. And I think that this is really what actually kind of what makes some of these collaborations really working very well.
So going back to sort of the funnel and thinking about the individual researcher, so when someone goes to work at Unilever, because that's the example that you know, how is it that they find where they will operate in this funnel? You said it's what they like to do, but I imagine there are more constraints than what everyone would like to do. Does it sort of settle out naturally over time, or?
Well, there are different ways in which, kind of, I guess, someone finds a job in a company. Well, either through kind of being hired at the beginning, I mean, of their industrial career, or later on, kind of.
I was thinking early on, because that's what most of the.
So I know that there are at least two schemes which are in operator in operation. One is called the graduate scheme, and I know that several companies do that. So they would look for someone who's just out of PhD, or their masters, they would train them in what the company does, and there would be some kind of like a rotation period. So the new graduate would try out, first of all, being tested and selected, so that only the best ones would actually join, based on what you know, but also how to operate. Because I think that one of the key things in working in a company model is being able to work in a team, and also being able to communicate across people who don't know your own background. So, I mean, after that kind of a selection, and then you join. I mean, and then there are schemes where the young graduate will be trying different things. So spending 3 months or 6 months in R&D, 6 months in more manufacturing, 6 months in the supply chain, and that helps making the decision of which is the best place within the funnel that you might want to operate. Of course, it's not automatic that you actually get that job, but then you clearly kind of understand what your preferences are because you try it, right? And again, that kind of helps you make that choice. Or maybe if you come in much later on, when you already have a clear idea of what you want to do, and you know exactly
your
what
expertise.
your expertise, you are hired to do a specific role, and that's kind of that's a different entry point. That's
I was thinking more about the earlier levels. So it's very dynamic.
In that case, yes, it is. And I've seen many kind of graduates come through our scheme. It's fantastic because they really, I mean, are very keen to actually learn that, and then say, okay, let me try something else now, and it's really great. Yeah.
Okay. But you do have, there is the subset of people who are working on algorithms and tweaking the codes so that someone else can use them. You still have that.
Absolutely.
There's that subset of people, which is what most of the PhD students are doing.
Yeah.
Right?
So again, I mean, and typically, I guess that of course, I guess it's depending on which company it is, but I would imagine that everywhere there would be the need for someone who's an expert in computer simulation, someone who's an expert at doing very complex calculations, and perhaps if that is the competitive advantage for that particular company, if this company is in kind of uses finite element analysis for their own business, of course their computational team would be a lot larger than another company where, in fact, that is not kind of their trade. So again, different sectors will have different priorities, but then I'm sure there will be plenty of space, specifically in some companies where this skill is specifically required.
And related to computational facilities, sometimes I think people want to do things quickly and turn them around.
Yeah.
Sometimes things take longer amounts of time.
Yeah.
So would Unilever or its competitors have their own HPC at some level? I mean, not the Hartree Center, but would they have those facilities in-house and invest in them? It is costly, or are they looking for someone else to do it, or are they?
It depends. Again, I mean,
they kind of try to minimize.
It's a very good question. It's a very good question. So it depends on the choice that the company makes. I guess. So some companies would want to have their own HPC in-house because I guess that they feel that they want to be in full control of the data, security of data, and being sure that doesn't leak out. Specifically, if kind of a data handling and data is your trade or something which is really essential for your success. Other companies might decide that, well, in fact, my trade is not doing computer simulation, is actually using computer simulations to do something else. But in that case, they would be a lot more relaxed and say, well, actually, let me actually work with someone who has got big computers. I don't want a big computer, I want a friend with a big computer, and then use the big facilities to help me do that. So again, I mean, I don't think there is a specific formula, but I've seen both things happen, and in different shapes.
And how about using other kinds of friends, like our friend Eric here?
Yes.
Who's in the business of, helping execute computation and use methods and, provide software.
True,
is that an active part of what Unilever engages in part of the partnership?
Yeah, so again, so I think that there's lots of interactions, yes, with academics, but also with small companies, and also translators. So I think that kind of one of the things which I think is now perceived is I mean, as a benefit, is that being able to translate how to do these very difficult computations into something that where people can use. And then I think that we have an example in what we've done for this prototype for Unilever. So making these complicated things easy to run for then the end user is really, I think, that the way that things are going. It's easier said than done because kind of making sure that this piece of code is used as it should be used. So you have to put boundaries, and then you have to make sure that kind of people don't use it to ask the wrong questions because otherwise it can do more damage than good. So that really is the hard bit. But if there is some training behind it, if the user is well educated, looked after, I mean, it can be done. And again, I think that there are examples where in fact, these packages have been used quite effectively in a simplified way, but then really kind of people use it to actually do their daily job, which is to make the new invention or produce that. The other thing which I think that is very kind of interesting, and then probably people are coming to terms with is that through computer simulations, one doesn't only get an answer, I mean a number in the end, but one gets the knowledge on the mechanism behind what is happening. What I've seen happening is that, of course, you do want a number in the end. You want kind of this is twice as much, right? But then the question the next day is, but why is twice as much? Because then if you know that, then you know the mechanism. So for example, this polymer has interacted with this other element in the formulation and then made a blob or did not make a blob or somehow. So that kind of a mechanism, it's something that you can only see if you have the luxury of having this molecular lens or mesoscale lens that tells you what is going on. And that's important for two reasons. One, you know the mechanism. Two, once you know the mechanism, you know what to do about it. And then three, kind of helps you map the IP space as well. Because if I know that molecule polymer X has that behavior because it interacts with this other bit, then I know how to secure my patent space in a way that I wouldn't before. So kind of people are more interested now, not just in the number, I think, but also in the mechanism, because that is the value of it. And in fact, much of the computer simulation, whatever scale you are, gives you that answer. And of course I would say that because I'm a simulator at heart.
Me too. How are we doing on time, Sarah?
I think maybe one last question. And then
Okay,
right,
yeah,
okay.
I was thinking we're having I had questions here, but we just kind of skipped through them all.
Of course.
So one minor thing about publishing, because again, for the students, the postdocs, right, who see publishing as sort of the be all and end all, and when you go into industry, so what did you find at Unilever in terms of the openness? You're talking about open innovation, and that means some of your partners do need to publish. So what do you think is the current trends in that direction?
Yeah, so I think that, again, I mean, it depends on the company.
Yeah, sure. I just get
it
your
depends
perspective.
on this, but I think that most often than not, kind of you can draw a line in the sand again, and then say, well, if it's something which if I've discovered something which is useful for the company survival or next product, of course I don't want to publish that, because that's something that needs to be turned into either a trade secret or a patent. Yeah, and then really, I mean, you actually make a new product and then you sell it, and then you want to prevent your competitor from doing that. In that case, if it's so specific as a molecule, as a process, as a new formulation, that needs to be protected. If it's something to do with maybe a new model technique or a generic application, again, I mean, I've seen that most often than not, companies tend to publish that. Well, for two reasons. One, it is a stake in the ground, saying, well, in fact, we are doing great science, and in fact, we want to attract people who like to do great science. So it's a great way
public
to
relations to the scientific community aspect to saying we do science.
We do science. We do great science. We want to work with people who understand that. And again, I think that kind of also opens the door to the right conversation with the right academics who are interested in in the great challenges. Because again, I mean, I think that if you're working with a real system, you do have incredible challenges, which are scientific challenges. I mean, how do I make an approximation? I mean, I have 20 ingredients, which are the important ones. Again, these are actually kind of very, very interesting questions to ask. And how can I make it as simple as possible? I mean, a good scientific question there as well. So I think that if you can publish to a degree, and in fact, I mean, publication is actually been encouraged. I mean, at that level because of these things. Because one, it kind of really it shows the scientific authority of that particular company, but two, also opens the door to conversations with the good academics, the ones that you want to work with, and they want to work with you. I mean, otherwise, because again, they see that they can speak almost peer to peer with someone who actually understands. I mean, how things are done, and also, I mean, it would be good to attract, you know, the next generation of people who want to work with you. And again, I think that having that kind of ability to publish, I think that. So I mean, I've seen that happening. I mean, and again, if you can draw that kind of a distinction between that is something which I'm okay to publish because of all these reasons, and this is what I'm not okay with publish, because in fact, it from the company perspective, it helps me more if it's either a patent or a trade secret. In that case, of course, you don't want to do that. But yeah, I think that there is a balance there, and in fact, both ways are currently used, I think.
Well, it sounds very healthy.
Yeah.
So let's get some other people involved in the conversation. So.
Very much, Massimo, for this
Right.
first part of the conversation. It was truly interesting. So just to inspire you, Massimo referred to a real-life example of a situation where you had
So there is one.
computers, the simulator, the application, and the final product. There it is. So with that backdrop, the floor is open for questions. Yes.
So thanks a lot for the talk, for the
Cheers.
conversation here. And regarding to open innovation, how do you see, or you see the materials modeling marketplace as a mechanism for that?
Oh yeah. So this is the initiative that I think is coming up from the European. Yeah. So yeah, I mean, I think that would be a nice way to actually provide kind of a selection, I mean, of possible tools that a company might want to use for their own research processes. I think that what could help there is making sure that if there is a marketplace for these specific tools, there is a way to actually guide the choice or guide, I mean, what are the pros and cons, essentially? Because I guess that making sure that one technique is better than another comes with, a lot of knowledge on how to use it. So I think that the best way in which that could be adopted is through kind of a very much of a personal interaction with what the company might want to use it for, so that it can actually help choose which one is the best tool on that tool set that you may want to build.
We hear a lot of the reproducibility crisis in science. How does it work for companies? Are there additional checks implemented now when communicating with academia? And would you say that losing hard cash in doing science is actually helping you to make more reproducible results in a company?
Oh, what do you mean by the reproducibility crisis? I'm not sure I understand that.
Well, there was a Nature biology that where researchers in companies conducted tried to reproduce experimental results. It was also published, I think, in high-level journals.
Yes.
And they found that 90% of these were not reproducible.
Wow.
And I also read something very similar happening in materials, but the numbers are much lower. So this is where my question comes from.
Okay. Wow.
But you haven't.
Well, that's horrible. Of course, yeah. It's definitely not where you want to be. So this is definitely not a kind of a scientific method. Of course, reproducibility should be there. I mean, of course. I mean, if you do find something, I mean, it should be well documented and reproducible, so that others can do that for you. Of course, in a company, this is even more true because, again, if
You have to make something.
if you have to make something and then you have to kind of take what you do and then pass it to one of your colleagues to actually work on it, it should be reproducible so that they can build on it. So what I'm aware of, at least in the company I used to work with, there was a system to actually codify the knowledge in terms of making sure that experiments are well written, summarized, and into a set of reports. But then the company I work for is acting as many companies as well. So there are, a set of internal publications within the companies which kind of codify that knowledge into a structured way, which, of course, would be nice if that knowledge was searchable, so that not only do you actually pass a set of decks to your colleagues for them to actually pick this up and then go forward, but also if you want to search what actually was done before my time, so that you don't have to redo it again and then rediscover the same things. So I think that kind of having, a very efficient way to codify the knowledge, so helps, in two ways. One, in terms of reproducibility. Two, being able to move it on to the next person, kind of taking this work on, but also being able to search all that knowledge in previous years. Because again, it would be nice to be able to search not just the PubMed, but also your own internal literature. That would be very helpful.
Okay, we have questions on the back. Could you pass the microphone? Thank you.
I was interesting about the aspect you were saying. You were giving that example that you would go to the floor downstairs and then you would get a question on some problem and then you would go up and just perform the simulation. And it's very interesting because it opens the question about how much freedom is in there. Also having experience in an academic environment to like pursue your own ideas and projects. How does it work there in a company? Is
so,
it
I made that comment
as easy as that?
Yeah, very, very good question. So, I made that comment because, again, I was trying to compare and contrast my experience doing my postdoc and then my first year, in industry. And in fact, in my years, in a couple of years, as a postdoc, I really wanted to work with an experimentalist to try and test what I was doing. And I had a very hard time to find one. Because we were not on the right length scales, or probably we didn't actually find the right one. So I actually personally found that kind of a difficulty. But when I joined the company, so there was a lot more of collaboration in that sense, in terms of trying out some of these models and theories directly for some applications, or actually helping each other. In terms of the freedom to operate, again, that is, I would say, within the range of the project. So if the project is to come up with a formulation which is higher viscosity, then that is the end goal. So I guess that kind of sets the boundaries for what the end goal should be. But of course, you also have some free time, so you can also explore things. But the main part of your goal, of course, should be to kind of collectively with the team try to get to that outcome.
And if I can add on that, so if you are in this beginning part of the funnel, the fundamental science, let's say the blue sky part, are you acting within this big project, or you have the freedom also to propose new projects and to push them up to the management?
So most often than not, of course, you are part of the project. But then again, would you be able to propose something new? Probably. Now, do I know a mechanism for doing that? At the moment, I can't think of one. But I do know that there are companies that in which this is possible. So there are kind of big gatherings, and then kind of trying to come up with what might be kind of. But that probably would be done by kind of field by field. So not just within the company, but in fact in collaboration typically with the research partners. There would be some exercises where you can say, well, in fact, if I really want to come up with the best technique to address that particular problem, what should I do? And in fact, out of that come out, or can possibly come out, new research projects in terms of collaboration with with academia. So these things do exist, but once I guess that the project is in place, that is probably kind of the main job that you will have to do.
Could you please pass the microphone behind you?
Hello. This is a question in follow-up with Bill's one of his questions. Is like you said, like when you have a project, a person is doing, or a group of people are doing this project, and you have this goal achieved, and then you pass it on.
Yeah.
The thing is that so this kind of appears to me kind of like a temporary thing. So is this done by temporary employees or like permanent employees? So because like if you give such things to a university, they can do the project, it's done, it's over. But for a permanent employee in the company, they should have a permanently something to work on. Otherwise, why are you paying the salary for? So what happens then?
Yeah, no. I think that kind of this flexibility on which project you work for is for the permanent employees. So everyone on their books, I mean on a company's books, will work on a project which has a beginning, middle, and end, and then the same people will work on something else afterwards. So you wouldn't deviate much on your area of expertise, but the particular molecule or the particular formulation that you're working for will actually change. And once that is complete, you move on to the next one. It doesn't mean to retrain yourself in something that you're not familiar with, but then that project comes to an end, and then you move on to something else, hopefully more interesting.
Thank you.
We have a question here at the front, and then you pass the microphone there.
So thank you very much for being here today. I have a more general question. So you said you did a postdoc.
Yeah.
And now we often hear it's better to just go directly. If you want to go to industry, it's better to go after your master than your PhD, even the postdoc. So what is your opinion on that? Like,
it depends on what you like to do. I mean, I would say probably the sooner I would say if you want to try out an industry, I would say the sooner you try it, the better it is, because then you know whether you like it or not. So I think that if you really want to try that out, I would even try and kind of go for a few months, say during the summer, see if you try and go for a placement of some kind, and then you see if that kind of like that environment. So I wouldn't wait too long before I do that. I mean, as a try. In terms of what is the best way, I mean, in terms of like the entry point for a career, again, it depends very much on what you like to do. So if, I mean, we talked about the different entry kind of pathways. If you are very flexible about, and you want to, I mean, explore what would be like if you are in the supply chain or in finance or in R&D, then I would suggest, why don't you join one of these graduate schemes where there are these rotations, and then you can try and then you can decide. But if you know that you like to do computer simulations, and you know that you like doing finite elements, or then perhaps that is your trade. That is what you like to do. So you want to do the master, the postdoc, the PhD in the postdoc in your field, and then just enjoy what you do. So your entry will be much later on, but then just to do what you like to do. So again, it depends on what you love, I think.
so did you find it hard in the beginning to find a job in the industry, or?
No, I didn't. So I mean, in my career path, I have been. Well, I mean, I was talking about this with Sarah today at lunch. So I've always been interested in surfactants, and then I did my PhD in surfactants. I did my postdoc again on self-assembling systems, and guess what? I found a job in an industry which talk about surfactants. So I've been quite lucky because that is kind of the system that I like to work with. And then when I found that, was it difficult? No, not really. I mean, at that point of my career, I thought that I probably kind of perhaps too late. I mean, I wanted to try things out and then see how things were in industrial. But I never looked back. I mean, I enjoyed it thoroughly. But I thought that was the right moment for me to try and do that. Just because I wanted to work specifically on computer simulations of these systems. And then when I joined the company. Then I started from there, but then I discovered that I might actually want to try something else. So I did actually explore different roles within the company. But again, I mean, it really depends, I think, on what you enjoy doing. And if you want to, again, if you want to try things out, I would encourage to try out as soon as possible. Maybe with a short kind of a risk-free period, kind of a 1 month or two, just to see if you like it or not.
Hello, thanks for your talk. I have basically two questions. First is that are huge companies, very, very big companies, are they inclined to get research institutes such as yours to solve their problems, or initiate their own R&D departments? And what's the borderline? What's the biggest company that has referred you for a question? Is the first one. And the second one is that I think there are some projects that are referred to you, and the institute couldn't succeed in answering the question. Can you give us a rough estimation of the statistic of failure and successes of such institutes? It's not specific for your institute, so basically I think there are other institutes doing such thing. Thank you.
Yeah, okay. So question number one is the type of size of companies that interact with SDFC. I mean, it varies from small to medium to big. I'm very familiar with the partnership that has been developed across Unilever and SDFC in the last 5 years, because it was on the other side of the fence when we did that. And that kind of course, that is one of the giants in the area of fast-moving consumer goods companies. And so that partnership meant that I mean, across the two entities, the private and then the public, there would be not just one project, but a series of projects. And that actually what made it really successful. So you could have projects both in the ideas phase, in the development phase, and also in the manufacturing phase. So I mean, across the board, there were a number of projects, so much so that both parties decided to really become partners in the long run. And that means creating some kind of a framework around that, so that they could actually interact much more easily, so that even when it comes to setting up a contract, there would be a fast-track way to actually do that. So that is kind of one example of a big company interacting with SDFC. But again, there are lots of examples of smaller companies and also startup companies as well. I mean, I showed the picture of the Dansbury campus. On that Dansbury campus, there are about 130, 140 companies that actually have a space, on there. And the size goes from one person, a very small company, to medium size, 10, 20, to actually big companies. And in fact, I mean, I mentioned IBM Research, which has almost kind of a big chunk of that kind of sitting in the same building as a hardware center. So again, I mean, big range of very, very small to medium to large. And then each one of them can interact with either Hartree or the SDFC in a different way. They claim, and in fact we do run like a survey every year, that in fact being close to such national scale facility helps them in getting more research done more effectively. So probably about 50–60% of them really, I mean, value that, and they decide to stay on campus because of that reason. And the other thing which happens, which is fantastic, I think, is that whenever a company joins the campus there, they make it kind of their home for life. So if they grow from one person to two people, they will be asking for a bigger office. So, but they wouldn't go anywhere else. They will stay here and ask for a bigger office. If from two people they want half a floor, they will want to kind of, and in fact, that picture that you saw there is actually going up the hill. And then as you grow down from one person, you would graduate going up the hill and then kind of renting more and more space. So in fact, we're actually just about to start building 3 new buildings, I mean, at the Dansbury campus, just because we're actually kind of filled with companies that want to really co-locate with us, and then they want to stay, whether they want to come and join or whether they want to grow. So I think that was the first question. The second question was about the failure rate. I don't know the numbers, I'm afraid. But then, of course, not every project that they actually do is successful. I think that the important thing is to make sure that along the way you learn why things work or why things don't work. Again, if in the end what's important is the mechanism of action, then I guess that learning that mechanism is already something which actually is of value. So whether polymer X works in a formulation or doesn't work, as long as you know the mechanism for why things work or did not work, I think that is kind of a good learning, because it would point you in the right direction, I think.
So would the management in Unilever see that failure is okay?
Oh, I didn't say that. I said that
Well,
it's important.
But if you're doing high-risk work, then some of it will fail, and so there's always this. No one wants to say it didn't work.
Of course, it is expected that of course, not everything that you try will actually work. But of course, the outcome needs to be something that actually kind of lets you go forward. So of course, you
so
try many things.
right.
You try many options. What I'm saying is that of all the options that you try, many will not work, but one hopefully will work.
Okay.
So you do want to have an outcome in the end.
So we have a few more questions, and I would like to take two more, and then perhaps close this session. Both Massimo and Bill will be with us for about an hour, and you will have plenty of opportunities to keep interacting with him. So we start from the question right there, and then we move to the front. Yes.
Yeah. So you have mentioned that the Hartree Center is like you have AI field. So my question is, in the industry, when there's some innovation happening for the research, so what's your perspective on this machine learning and data science?
Yeah.
In particular with the physics and the chemistry in the spectrum of the industry product?
Yeah, very good question. Very good question. So I think that looking at kind of a data science approach to problems is very valuable, especially because it gets to an outcome very, very quickly. And then sometimes it's the only thing that you can do. So, for example, suppose that you're trying a new formulation, new product, that in the end, after many iterations, will actually have to have an effect on your hair, right? There's so much rope between the ingredients you put in and then the final outcome that sometimes it's almost impossible to kind of use physics and chemistry to build up all those links. So again, one quick way to actually try and correlate your inputs and your outputs is only through kind of a data-driven approach. So sometimes kind of doing this correlation really helps you bypass all of that. So you get an answer very quickly, and then you know how to correlate inputs and outputs, which points you in the right direction. You don't understand why, because it's just purely kind of driven by a correlation. On the other hand, if you can combine some of this data-driven and some of the understanding through classic simulation, that probably is the best of both worlds. What I've seen, in fact, now is in fact probably the value is in combining maybe machine learning type of approaches, guiding, for example, a set of simulation. So you could, for example, look for a new molecule, new formulation, just by exploring linearly a set of different options, which is okay, because you can do this all in parallel. But you can be smarter than that and say, well, in fact, let me start somewhere and in fact run a few simulations classically, whether they are atomistic or mesoscale or whatever, and then in fact analyze the outcome and use that as the input for the next round. That actually gets you to the solution a lot quicker, and you don't have to explore everything. So there are ways in which you can use the information that you gather in these hotspots to guide you to the next choice. So I think that again, I think that the best of both worlds would be to combine data-driven approaches, i.e. machine learning, to guide what is the next simulation batch would be. And there is a number of people that actually are going down that path. So I think that is really, I mean, a hot topic at the moment, and something I would definitely watch.
Last question.
So STFC is in the UK, right? So do you think that the Brexit, however it ends, will have an influence on your working
That's
situation?
a very good question. Yes, I mean, I don't know. So STFC is the Science and Technology Facilities Council for the UK. I mean, it's part of a number of founding councils. There is the Medical Research Council, the Physics and Engineering Council. So STFC has a unique role to look after the facilities on behalf of the UK. Whether which Brexit or whether or not Brexit will happen, I have no idea. I mean, I wish I could, because if I knew how to predict that, that would actually tell me what I could do before that. But no, I mean.
But do you feel it right now
honest
already?
Answer, I mean, I don't know what the impact.
But there's no change right now that like less companies ask for help or whatever.
At the moment, I mean, I can't see that I see any differences. But again, I mean, what the outcome would be in the future, I wish I knew, because if I knew, then I could actually bet some money on the right side.
Okay, thanks.
Okay, so I would like to thank Massimo and Bill for this conversation. And I would also like to thank you all for making this such an interactive and pleasant experience for all of us. Now, there will be more of this type of conversations. We haven't really decided what's next on the agenda. So please stay tuned and follow us on Twitter, both on Cecam and Marvel Twitter, is just to see what is going to happen. It's probably going to be something in the fall. Okay, with that, I think that we can close this session. Thank you again. Thank you to the speakers. Thank you all. And as I said, Massimo and Bill will be around for about an hour, so feel free to keep asking questions. Thank you.
Yeah. Very good. No.